Welcome back, and let's get into PSPICE. So this is going to be at a pretty low level, but it's going to be really important when we start getting into capture at the higher level doing the GUI, when we want to customize things and try and get our models to work and to tweak them to actually match our real world hardware. So hope you follow along and enjoy. So this tutorial is not going to go over capture. It's going to go over just the PSPICE code, documentation, making an example circuit, and running some simulations and viewing some waveforms through the command line interface. So for the documentation, you can get into it through the capture help menu, but I kind of like to use PDFs. So you can go here and just do PSPICE manual. You'll notice the first thing that comes up is actually this unofficial one from University of Pennsylvania. So it's actually better, though, in a lot of respects than the official one. Anyway, you're going to want to get this one here too, the PSPICE reference guide. So this user's guide and the reference guide. And then there's usually one like this one is not 17.4, it's 17.2. The official Cadence one, but this will be good enough. So the first thing you want to know about PSPICE is it's case insensitive. So it doesn't matter if you use capitals or lowercase letters. It's all the same. These are the basic elements here that you use. So R is for resistor. It's all about what letter the line of text starts with. C is capacitor, L is inductor, D is diode, Q is transistor, and X is for a subcircuit. And then I have this note here. If you look at page 49 of the reference manual from UPenn, it's got a whole lot more of the parts listed here. So you've got standard ones, but then here's like a transformer core, N-channel JFET, there's M for MOSFET, and all kinds of stuff. So all of these have their own fancy models with the complicated equations and a lot of coefficients, so you can customize the exact parameters and match it to real-world parts. So to customize those parameters, we can go up here to the previous page, page 48. This talks about defining a model. So you write .model at the beginning of the line. Then you're going to have two names right here. So the first one is the name that you're giving this model, and then this one here, it's kind of like an inheritance. So this is another model, which it'll use all of the parameters of this one unless they're overridden by these values here. So you can kind of build off of them from the default model. And then these are all the parameters with the name equals value separated by spaces. So if you want to model a diode, for example, here are all the parameters you can customize. Luckily, manufacturers often have diode models pre-made, and there's a lot that are built in to PSPICE, so you don't have to really customize these that often. But it talks here about all the different equations and how those parameters are used. So after the elementary parts, let's check out the sources. There's two super basic types, the voltage source and the current source. So that starts with a V or an I. And by default, it's just a DC source. If you just put like a number after it, it'll be the voltage or the current. But you can also put tags after that to give it like an AC source or a pulse source. And AC is for an AC analysis. And then there's these four types here, which are controlled sources. So this E is a voltage controlled voltage source. The F is a current controlled current source. The G is a voltage controlled current source, and the H is a current controlled voltage source. So those have an equation that defines the output voltage or current based on other voltages or currents in the circuit. And since you can define their voltages and currents with an equation, that allows you to do what's called behavioral modeling, or analog behavioral modeling, ABM. And what that is when you use a controlled source to model something behaviorally that's not necessarily a discrete part. So in this here is an example of what you might do if you're linearizing a power converter and you want to model the PWM chip creating a duty cycle. So you can represent the duty cycle as a voltage between 0 and 1 volt, and then you can have an equation that calls other voltages in the circuit and calculates the duty cycle. So you're modeling the behavior of the PWM chip and not the actual circuitry of it. So to look at what you would put in the equations, the most basic thing is numbers. So this here is a little table of numbers. You can put them in with exponents, but it's easy to use engineering notation. You can put F for femto, P for pico, N for nano, and these are not case sensitive, so you can use large or small letters. You can do M here for milli, so you have to do MEG for meg, and then gig and tera. The other thing you can use is all these built-in math functions, so absolute values and sines and logs and all that kind of stuff. So there's a whole list of the different ones you can choose from here. And beyond that, you just use voltages and currents. So like in this example here, you can type V and then the name of a node. And you could also put I in these brackets and the name of a node. Or you can use the name of a part to get the current or the voltage. Then once you get all your elementary parts down, you can wrap them in a subcircuit. And that's a way of kind of avoiding redundancy or making a higher level type of part, like an opamp. It's a good example. You can have a subcircuit that represents the whole opamp, and then you can use it in multiple different places in your larger circuit. So the subcircuit starts with this .SUBCKT parameter, and then it ends with this .ends parameter. And in the middle here, also notice if there's a plus with a space at the beginning of the line, that is sort of an extension of the line. So this is equivalent to getting rid of this and moving this up to this line. It's just a way to break up really long lines. And the other cool thing about subcircuits is you can put this params thing on the top here. So you write subcircuit and then the name of it, and then you have the lines coming in and out of the subcircuit, and then params, colon, and a list of parameters that go name equals value. And that way, when you're defining these circuits later, you can give it different parameters here. So you can have sort of one template for the part, like the op-amp, and then you can pass in at each definition of it different parameters, so you have sort of custom versions of each one in different places in the circuit. And the other thing you can do with subcircuits is you can wrap elementary models in them. So the dot models, you can have a regular part with a dot model, and then you can parameterize that part by using this subcircuit with the params, and then these guys can be the parameters inside the model, like a BJT, for example. And in that way, you can instantiate different BJTs in your circuit that have, using this wrapped subcircuit, and give them each their own parameters. If you just have like one parameter that you want to be able to change easily, like the VBE or the beta or something like that. So since we're not using the GUI, I went ahead and drew the circuit. You could draw it by hand on a piece of paper. I did this in Visio. And this is just going to be a simple demonstration with this 741 op-amp here. That'll be our subcircuit, and then we'll have 2 resistors and a capacitor and these 3 voltage sources. So these 2 you can see are connected over here to the VCC and the VEE, and then this one is going to charge this capacitor to flip the state of the op-amp. And the way that we're going to set this is with this initial condition of -5 volts here. So it'll start off with the positive below the negative, so it'll be low, and then as this capacitor charges up, the positive will go above the negative, which is tied to ground, and then the output will flip high at some point. So these right here are representing the node names. So since we're lazy and we don't want to make our own op-amp model, let's go on the web here and check out LM741 op-amp PSPICE model. Let's see what comes up. So hey, it's the last thing I clicked on. So if you go to TI's website here, you can scroll down and they've got right here an LM741 model, so we can download that. So here's their model. You can see all this stuff that starts with a star. These are comments, so it's going to skip all of this. And then down here, sometimes I do this kind of nifty action where you have comments with a little line coming down. This is where it actually starts, subcircuit. So here's the name of the subcircuit, and then these are the input-output pin names. And these names correspond with nodes that are down here. So there's a lot of different parts here inside of the subcircuit. And then it ends with a .ends, and you also find the models of the parts that are used within the subcircuit at the bottom. And just to be clear, these node names can be numbers or they can be letters or a combination. We'll go ahead and write our netlist here in Notepad++. Note that what Capture does when it writes the netlist is it splits it into two parts. So it has a .cir file and then a .net file. And the CIR is like the simulation setup, and the net is where the main custom part of the netlist is, and it also links a whole bunch of external libraries. But we're going to put everything in this one file. So I'm going to call it all.net, and that extension is not really relevant. So the first thing we want to do is go over here to our model we downloaded, and we can just copy that, and we'll just put it at the bottom. So make a few spaces, and we're just going to leave it as it is with all the comments and everything. And then here, let's see if we can see our circuit over here. We're going to start off by defining the voltage supplies. So this one here we'll call VCC, and it's going to be a voltage supply because it starts with a V, so that's important. This here is just its name, but this first one has to be a V. And then next we give it the nodes, and you also have to be careful that you do the polarity right. So you have to check with the manual sometimes if you're doing this by hand. So for here we do the top of it as the first node, so this is going to be VCC, and then a space, and then 0 is our ground node. And then we just put the value, which is 15 volts. So the next one is going to be VEE, and that's going to go from VEE to 0, and it'll be negative 15 volts. And then we have VIN from in to 0 at 5 volts. So next we're going to define the resistors. Now the capacitor. So this is C1 from P to 0, and it's 1 microfarad. The resistor is actually the polarity didn't matter, but this one does matter because we're going to give it an initial condition. So we say IC equals -5. So that's, you can put just -5 or 5 volts. It'll ignore the V. So the way that these units work on here is they're pretty much ignored. So what it does is it looks for the first non-number, the first letter, and if it's one of the multipliers, like this U or this K, then it multiplies the number by that. Otherwise, it just ignores it. And anything after the first letter, it totally ignores. So like 5V, the V doesn't do anything, and then this F here doesn't do anything. So you can write whatever you want. It'll just ignore that. So to add in the subcircuit, we want to call this guy's name, and these are the different inputs here. So it's the non-inverting, the inverting, the positive, the negative, and the output. So since it's a subcircuit, it has to start with an X. So we're going to call it X1 for its name. And then it's the non-inverting, the inverting is ground, and then the positive is VCC, the negative is VEE, and then the output is just out. And then its name is, we'll just copy and paste its name here. We'll save that. So back at the slideshow here, let's mention a couple more things about initial conditions. So we used an initial condition to set the capacitor here to 5 volts. And you can do that for a capacitor or an inductor. For a capacitor, you're setting the voltage. For an inductor, it's the current. But you can also just put a .IC anywhere in the circuit and you can set a node voltage to a certain value. And that's for the beginning of the simulation, which is the bias point calculation, which is also the bias for an AC analysis. The other thing you can do is you can use this node set. And what that does is, because you're doing a least squares style iterative solution, you have to begin with initial conditions to the solver. So we'll have to talk more about how the solver actually works in future videos. But the difference here is that this is the initial condition sort of to the solving solution. So this is not going to be the bias point value. This is just something to help it converge. So you can use these guys to help it converge and these guys to set a fixed bias point value. And then the other thing you can do here is you can have it automatically save a whole bunch of these .IC values as sort of the whole circuit state. And you can do that with these keywords here. Save bias, give it a file name, and then it'll just dump out a text file with a bunch of initial conditions that save the whole state of the circuit. And then you can do this load bias later. So that way you can run a simulation, save the circuit state after it's been running for a while, and then use that as the beginning point for a later simulation or series of simulations. So you don't have to get to steady state every time you want to analyze something, for example. So now that we've got our circuit set up, we just need to define the simulation we're going to run. These are the 3 most basic types right here. And this is the DC, the transient, and the AC. So the DC is the precursor to both of these. You can't start a transient without first establishing a DC bias equilibrium for the circuit. And then the AC, it runs pretty much just on that DC bias point. The transient uses the DC bias point as the starting point, and then it calculates each step through time from there and creates the waveform over time. Now there's also this options command, which lets you set up options for the simulation settings. And this we'll go over more later. This is what you're setting up when you're doing the simulation settings in the GUI. And there's all these different parameters, and these are mainly to help your circuit converge with the solver. So ours is so simple we don't really have to worry about these values, but it also lets you set some things like default temperature and stuff like that. So if we go to the documentation to write a transient analysis, you just write .tran, and then the simplest way is just the start and the end. So let's get a couple more lines going up here. We can clean up the bottom of this. And we're going to write .tran, and our start's going to be 0, and our end is just going to be 1 millisecond. And the last thing we want to look at is which waveforms we want to save and how we want to save them. So the first option is this .dat file here, which is a binary data file, and you use the probe tag for that. And this is what the GUI uses and what we're going to use. These are a little bit legacy right here. This is to output to a text file, and either way we're going to get this .out file, which is sort of like the log file, but you can also add more information to it. So you can have it print the output waveform as a text table in that .out file, and then you can also use this .plot, which adds sort of a funny little drawing using text, which I'll show you. So we want to do .probe, and the 2 nodes we want to look at are VP and VOUT. So that's the signal coming in and out of the opamp. And then because these are not numbers, I guess, you have to use these square brackets around these guys like this. So now we'll save this. To run this file, we've got two options here. So there's the command line version here, which is this executable PSP_CMD.exe. And then there's the actual program, which is the regular one that you use when you click play in Capture, and that's PSPICE.exe. So we'll send this netlist to both of those, and we'll see what happens. So first we want to change directory to where we wrote our netlist. And we want to send it. If you don't have these guys on your path, you got to give it the full path to these files. So then afterwards you have these tags, and these are kind of the minimum ones that you need for this. -R, and then the netlist, -D, and then the dat file, and -O, and then the output file. So now let's open up a command prompt. We're going to type CMD in the Windows search box. From here we want to change our directory with cd space, and then we'll copy and paste in our working directory. Now I'm just going to copy and paste the text from that slideshow. So this is the path, full path to this PSP_CMD.exe. We're giving it the R flag with our netlist, and the D flag with the name that we want it to save the data file, and the O flag with the name that we want it to save the output log text file. Hit enter, and so that ran. And here is our new output file here. But the dat file didn't seem to appear. We look at this, there's nothing really wrong with it. So to get it to work, I ended up having to add this extra line here, which links in this nom.lib file, which you'll notice is included by default when you create a capture simulation profile. So now if we save that, bring up our command prompt again, and press the up arrow to run, here we get our output file and our dat file. Now if we open up PSPICE 17.4 A to D, we can drop in our dat file. And now it'll open this up. If you hit the insert key on your keyboard, then you can type the name of the signal we want to look at, and you can see there's only two to select here. We have the output voltage coming along like this, and then the output switches right here when this input voltage crosses 0. And that was because we had the negative of the opamp tied to ground, or 0. So now let's go in here to our netlist, and we'll just activate these print and this plot guy here. We'll start with the print one, and if we rerun this, we can see in our output file toward the bottom we get this whole table. So this is the waveform outputted in text. So that'd make it easy if you wanted to copy and paste it into Excel or something like that. So to check out the plot, that one looks like this. So it actually does the same table, but it makes this little text waveform here. You can kind of see, I guess it's sideways really. So if you tilt your head, then you can kind of see it. Here's all the time column right here. So each one of these is giving you a voltage here, but also giving you the picture going up with the voltage positive this way. Anyway, the next thing we can do is just call the same thing, but instead of calling our PSP_CMD.exe, we can just call PSPICE.exe, which is the GUI program. If we run that, then it pops up PSPICE automatically and shows us our two waveforms. So that's all for this tutorial. There's obviously a lot more commands and stuff in all those manuals, but this gives us an overview, just You really need to understand a little bit of behind the scenes, because Capture is just a layer on top of PSPICE, and if you don't understand what it's trying to do, then if you run into problems in Capture, you really aren't going to be able to figure out how to customize anything or get it to work. So hope that helps. We'll get into the GUI next time, so I'll see you then. Thanks for watching.